Spoke at the conference. Thanks, Russ. In 2017. And so today I'm going to talk a little bit about my dissertation, which is in analyzing movement dynamics in elite female soccer athletes. And this is in collaboration with the Applied Physiology Lab at UNC, which is in our Department of Exercise and Sports Science. And so feel free to drop any questions in the chat as we go, and then I'll try to answer them at the end. But to start, I'm going to give you some definitions and some facts. So athlete availability is defined as the unrestricted capacity to participate in training and or competition. And this is the single most important component for individual and team success. And athletes who complete at least 80% of training sessions have 7 times greater likelihood of achieving success or performance goals. And those were defined to be something that was defined athlete specific and team specific at the beginning of the season, depending on what sport they're in, such as a race time or a finish position. And then with training accountability availability accounting for 86% of this success in their season. And so we see that injury accounts for about 77% of athlete unavailability with, sickness and other things like that, being that other uh, percentage that's left. And so one of the gaps that I'm trying to fill is that all of this existing research is either male and female studies or specific to male athletes, and there are very few female specific studies. And so my work works to bridge that gap. And so where to start? Women's soccer is kind of where we're going. So I played soccer in college, and this is something that's super important to me, but also with the recent rise in female soccer players playing professionally, we've seen an increased need to understand what aspects are important for training and success at this level, beyond, college into the professional leagues, whether that be in the United States or overseas. And with that, external load monitoring has become very popular in soccer, not only, but all other sports as well. You can see this girl is wearing what looks like a sports bra. It's actually a heart rate monitor or a GPS unit, depending on what teams have, that monitors their external load. And it's a common method to quantify like how much volume you're putting into training, specifically for soccer, just because you run so much up and down the field. And then we can look at kind of how this affects our performance. And so to overview our study, our goal is to quantify movement patterns and to explore the relationships with player performance and health outcomes. So our data included daily measures and periodic measures. So we have a daily wellness survey that players figure out or fill out on a Likert scale. So it ranges from -3 to 3, with positive scores denoting the positive outcome. So for example, if their soreness was 3, that would mean they were not sore at all. A soreness of -3 would mean they were the most sore. And then we also, one of the unique components of our study is that we are including menstrual cycle information. So we look at their menstrual cycle, as well as units of contraception, which is very rare in female sports just because of, the health concerns that this data does have. And so then additionally, we have their daily training load, which is computed by the wearable accelerometer with the GPS data. We have sports specific performance. So we have their individual and team outcomes from box score stats. And then we also have some KPIs that are for physical and technical testing that they do throughout the season as well. And so the main issue that I am working to tackle to start out with is that no matter which company you use for your wearable devices, whether it be Catapult, Polar, Player Data, some other ones out there, we note that they are kind of a black box in terms of what they give you. So they give you a training load number that takes into account the duration, distance, time spent at certain percentages of your max speed, accelerations, decelerations, sprint events, those types of things. But none of these companies actually publish how these numbers are kind of come up with, as that's very proprietary to their company. And so you can imagine when a team kind of changes from one company to another, they're kind of then having to relook at their numbers and redetermine kind of what goes into them and how um, they can then tailor their practices and games to those numbers. Because, for example, one company may say you don't want to go over 2,000 points in our training session method or training load method in one week, whereas another company might say 500 because of how they compute their numbers. And so when a coach tailors a practice to the one device they have, then they switch units to another company. It's really hard to go back and forth in terms of understanding what those numbers can mean. And so our goal is to then, can we break down this player training load into key identifiable components that are used from the raw data so that no matter which company you're using, no matter what data you're looking at, as long as you have that raw data, you can come up with a way to understand the player's training load. And so then from there, we had data from elite female soccer athletes, which so we had 9 athletes that played across 2 halves of 22 matches. So basically, we filtered for only players that played over 25 minutes a half in at least 5 matches over the season. We could definitely look at decreasing this threshold as we go, but to get a kind of methodology, we wanted to make sure we had enough data that we would be able to tell something from it. And so we basically have 1 point per second capturing the longitude and latitude coordinates of each player's location during play. And so this is kind of a mock-up of what the data set looks like in the raw data. So you can imagine for every second of every practice of every game, for every player, we have data that looks like this. And so that's going to be tons and tons of rows of data. And so to start out with, we converted the longitude and latitude coordinates to XY coordinates in meters, just because that's going to be easier to work with and understand. Since typically we measure, speed and acceleration in meters per second squared, that type of thing. So then from there, we fit a third order interpolating spline to the athlete's movements. So you can see here, we're fitting that line through the data. And then from there, we can calculate the velocity, acceleration, and angle using the first derivative. If we go back to kind of our calc days, the first derivative is going to be our velocity. The second derivative is going to be our acceleration. And then we were able to threshold some of those down to 0 just to make it a little bit easier. And we also did a log transformation to correct some skewness in the velocity and acceleration. So from now on, when I refer to velocity or acceleration, I'm actually referring to the log corrected version. But it's just easier to kind of refer to those as our velocity and acceleration. And then lastly, we took the difference between the angle for velocity and acceleration, and we looked at that mod 360 and then shifted it between -180 and 180. So it represents basically turning all the way left versus turning all the way right, so that we can get an idea of the direction of those movements as well. And so this spline just shows the first 50 seconds of movement for one player in a game. So from there, we defined what we like to call our data object, which is our quantile cube. So from our full data set, we established 5 quantiles for velocity, 5 for acceleration, and 4 for movement angle. And from these boundaries, we then construct this thing we're going to call a quantile cube for each half of each game for each player, with dimensions for velocity, acceleration, and angle. So if we take a look here at our cube, our x-axis represents our quantile of velocity. Our y-axis represents our quantile of acceleration, and then the little triangles actually represent our different angles of movement. So if we look at our Q1 here, that represents going forward, and this represents going right, and then going backwards and going left. So for example, if we look at this top right corner here, the density or the shading represents the proportion of time that we spent running forward at the Q5 level or 5th quantile of our velocity and 5th quantile of our acceleration versus moving right or left and those types of things. So we can see, like in this example, that in the second half, this player spent a lot more time at lower quantiles of velocity and acceleration compared to in the first half. And this is actually a trend we see throughout all of our data set, which I'll talk a little bit about more later. And so then now you can think we have n quantile cubes, each of a flattened d equals 100 dimension because we have a 5 by 5 by 4. And each entry in the d dimensions represents like the count or proportion of time that the player spent in that quantile of movement. And so we can actually express these observations using a Dirichlet multinomial distribution. And so if you're not familiar with this distribution, basically a multinomial is often used to represent counts, and the probability is kind of the probability of being in that specific triangle in our case. However, when we add the Dirichlet to our multinomial distribution, we allow those parameters or the probabilities of being within each triangle to actually be represented differently by certain covariates, such as the amount of time they played, the position, the player, how depending on how specific we want to get, because we don't think it's a very accurate kind of assumption to assume that all players move with the same probability of being within each triangle. And I think anyone who knows sports knows that's going to be different for every player. And so because of this kind of over dispersion in our data that we see, we're able to then model this with the Dirichlet multinomial distribution. And I'm happy to talk more about that if people have questions. But now let's get into some results. So if we use the Hellinger distance, which is basically a similar to an L2 distance, but we have a coefficient in the front, um, we can actually see a statistically significant difference between the distribution of movements for the first half and the second half for each game for each player. So this is just for one player, but you'll see we can do kind of a simulation of based off of the probability of being in a certain triangle from their actual game and the amount of time they played to see where we would get a null distribution using a Bonferroni correction. And then we can also see where the actual distance was between their first and their second half. So we took the Hellinger distance between the probability distribution from their first half and second half, and that's the actual is in the red and the simulated is in black. And so you can see we see this trend where all of the red ones are higher, which means it was a statistically significant difference. And we saw this across all players for basically all games as well. And then diving in a little bit more, we can use principal component analysis to reduce our 100 dimensions into about 5 components that explain about 71% of our variance. If you wanted to go higher than that, it kind of tapers off. So that's kind of the threshold that we got where without, gaining a ton of components to explain more variance. But we can actually see that PC3 specifically is one of our principal components, identifies a game specifically that resulted in a season-ending loss. It exhibited higher proportions of time spent at low velocities with high acceleration. So Q1 and Q2 of velocity where we had Q5 of acceleration. And you can actually see this here with the PC3 loadings. So we see in the loadings, we see very high loadings. These are the top 10. We're all in like pretty low velocity, high acceleration for all different angles. And we can see this even further in looking at the histogram of the PC3 scores. So if you isolate this one game, which was actually their last game of the season, they all are much higher than the PC3 scores for the rest of the game. And so we can hypothesize as to why this is true. Obviously, we don't know for certain why this is, happening, but some hypotheses are this game was played at a higher elevation than a lot of other games, so maybe that played a factor of players getting out of position and then needing to get back into position. So that's why we see that sudden bursts of speed. Additionally, they were up 3-0 at halftime and ended up losing 4-3. So maybe that played a component in why that game was so different than other games. That was the only game that was like that. So those are some hypotheses, but we don't, exactly know why that is. And then lastly, we can use the Dirichlet multinomial regression model. So we have our Y matrix that gives all of our observed counts for the N samples. But we can also define an X matrix, which has P covariates of the N samples. So we're going to consider covariates things like our half, our position, some of those daily measures that we have from the players. And so we can now assume that these parameters depend on these covariates with a log linear model. And we can then fit our Dirichlet multinomial regression model with covariates of half position group, so defender, midfield, forward, and soreness rating 2 days before match day. And so typically we use 2 days before match day because that's most indicative of performance on match day from literature. And we measure these on a Likert scale of -3 to 3, so 3 representing a positive outcome of there not being sore. And so if we look at the coefficients, note that the ones that are non-significant are grayed out. We can see that in the second half, we're spending higher proportions of time in these low quantiles. So Q1, Q2 of acceleration, Q1 of velocity, and we're spending less time at these higher quantiles in the second half, which is mean you would kind of expect that as players get tired. They're not going to want to run as fast as often, that kind of thing. Additionally, we can see that when we look at the coefficients for position groups, the baseline category is defenders, so these are all compared to defenders, but midfielders and forwards are playing, spending less time everywhere compared to defenders. I think This is mainly because defenders are typically play more, you sub them the least or not at all, whereas your forwards and your midfielders are going to be subbed out at higher rates, which is, this is in line with what we would expect. And so we're looking now at how we can control for time to see the positional effects as well. And then lastly, which I think is one of the more interesting ones, if you look at the MD2 minus 2 soreness coefficients, remember that a positive coefficient means you're not sore, a negative coefficient means you're very sore. So if you were more sore, you're going to spend less time in these higher ones. So because you have a negative score, you're spending less time here. And if you have a positive score, you're spending more time here, or more time here, sorry, versus vice versa. So if you have a positive score, you're spending more time in these high velocity, high acceleration zones. And if you're more sore, you're going to be spending more time here, which is, I mean, what we would expect. But I think it's a good kind of sanity check to see that we can see these representations in our data. So far, all of our results kind of align with intuition, but it's good to know that this model's representation can be used. And so then our next steps would be to create a baseline Dirichlet multinomial model per player to kind of get a residual per game for each player. And then also to be able to calculate our quantile cubes for practices 1 day before, 2 days before, and 1 day after a game, and then use those as input for our DMM rather than the scores that players are giving themselves. And then lastly, we can use our DMM output into a logistic regression model in order to predict injury. So I realize I threw a lot at you, but if you have any questions, let me know. And then from there, we can, I can also answer questions another time. Cool. Any questions? Yes, Jessica.
I keep asking a lot of questions, so thank you for the
No
opportunity.
worries.
Um, uh, so my, and I apologize if I missed you saying this. It looks like
No
all the
worries.
visuals are being created in R. By the way, the visuals were amazing. That really helped my understanding of features of your analysis. Were they created in R?
They were not. They're actually created in Python using ggplot.
Oh, yeah. Okay. And can I ask, I'm not familiar with the grid plot that you were showing or the square plot. What is the name of that plot?
Is the one you're referring to the one that was representing a quantile cube?
Yes.
I don't know if it has a name. I created it basically
Oh,
by like cutting things into squares and categories.
that is
Um, it's
spectacular.
basically like a heat map, kind of, but like with different areas.
Mhm. All
Um,
right. Well, sorry.
oh, you're good. Russ, do you have a question?
Yeah, Kendall's really good at what she does, Jessica. Question, this is purely hypothetical, but it's a little self-serving for me and it's a little self-serving for you. Um, what would this analysis look like if I said, hey, you've really got to do the same thing, but with goalkeepers, right? So there's less movement, I get that.
Yeah.
But there maybe, because it's been on my mind for a while, just an analysis of not necessarily the physical movements, but the stress or heart rate or
Yeah.
well, I'll stick with stress, right? Stress levels on goalkeepers.
Yeah. So, I mean, I will tell you, the goalkeepers in this analysis don't wear monitors because you're the device.
Right.
Basically, the team has a certain number of devices, and the coaches choose to prioritize field players, which I think is a fair thing given like you have X number of monitors.
Right.
When I was played in college, I was a goalkeeper and I wore a device. And I basically ended up running between 3 and 5 miles every game, which will like very much surprise you if you know like goalkeepers. But I mean, it's all the little movements add up, I would think. But I don't know. I honestly think like the analysis wouldn't like the same process we could use, you would just have to add the control for the goalkeeper. But I think it would be very different in terms of your results.
Yeah. No, I was just curious. It's been a project on my mind for a while. But
If you
okay,
have the
so
data, I would do it for you.
what's that?
Said if you have the data, I'll do it for you.
Oh yeah, that's a whole nother story.
Yeah.
Yeah, we should probably get going on to the next talk then.
All right. Well, I
Thanks
can
again, though. That was really good.
thank you. I'm happy to introduce our next speaker. Samuel is our next speaker, and his project is titled The Trade-Off Between Offensive and Defensive Actions in Different Phases of Possession. And Samuel's originally from Ghana, West Africa, and is currently in his final semester in his Master's of Business Analytics program at the University of Iowa. He's a lifelong connoisseur of the beautiful game of soccer and is deeply passionate about leveraging data and analytics to explore and enhance the sport he loves. So, Samuel, if you want to go ahead and share your screen.
I'll quickly share my screen right here. Thank you, Kendall. Um, a little challenge over here. Okay. Yes. So I believe you can all see my screen.
Yep.
Okay, fantastic. Um, today I'll be talking about possession value in different game phases, and it's actually an honor to be here to speak on this issue. I've been very much interested in analyzing possessions in games and what have you. Um, So I'm excited about today. So coming from Ghana, a country where soccer isn't just a sport but a passion, which is deeply embedded in our culture, I've always been fascinated by the beautiful game. And to me, soccer is not. It's more than just the goals. It's about the intricate actions that delves into the nuances. And I am very happy to use data to uncover some of the few things that happens on the field of play with regards to possession and how we can value possession every step of the way, from a pass to a carry, and also to some defensive action on the pitch. Now, um, now let's start unpacking possession value, and I believe this concept has been there for long. Some of you probably have heard about it, and that is not a new thing. But to those who have never heard about it, let me just give you a gist of it so that you get some background knowledge on it before we delve deeper into the overall analysis. Let's take two scenarios. There is a scenario where a player makes a very fine and beautiful pass that eventually leads to a goal scoring opportunity where it ends up being a goal, and everybody is happy about that. And there's another scenario where a player makes a very brilliant pass but end up not ending in a goal scoring opportunity, or the player who receives the pass did not make good use of the pass. In these two situations, most often, people tend to eulogize the player that made the assist for the player to score a goal, but they tend not to praise a lot players who make fine and beautiful passes, which eventually does not end up in a goal scoring in a goal. So in this case, this analysis is going to look at every specific and every action on the field that leads to a goal scoring opportunity. So that is essentially the brains behind possession value. And I think soccer is a game of moment, but the traditional metrics like goals and assists only tells part of the story. So my PV metrics, or the PV model I've developed, is designed to quantify the hidden contribution within the game. It measures the probability of a team scoring during any possession or action. It is there are a lot of names given to this possession value. Others call it expected possession value. It's also called the value added by estimating probabilities. It's also known as the on ball. So essentially, they mean the same thing. All of these names mean the same thing. But in the course of today's presentation, we'll be taking a critical look at the expected threat, which is the same as the possession value, trying to value every single possession on the field of play. So if you hear me saying a lot of XTs or expected threats, what I'm trying to say is I'm trying to evaluate or estimate the probability of a team scoring from every single possession on the field. So that is it with this possession value analysis. So, sorry. So let's take a look at what constitutes a good possession. Here, a good possession is the type of possession that moves the ball purposefully with intent of scoring a goal. The essence of having possession is the angle, looking at the angle, hoping to score a goal and trying to progress the ball gradually to a place where you feel comfortable and you are able to score that goal. And also, a good possession is a possession that looks into some loopholes in the defensive setup, creates some unique space that makes some that creates some great shooting opportunities and shooting goals and all what have you. So and also a good possession is one that makes a very quick transition from defense to also attack. So this is the backdrop of what we will be delving into in the next slides. So now let's talk about the model I used. There are a plethora of models that are being used in determining the value that have been assigned to some actions on the field. There are a lot of them developed by Sarah Rood, who came up with the Markov chain to predict possession value. And in recent times, we have guys like uh, um, Sign, who did a presentation during one of the StatsBomb conferences and also came up with the expected threat possession value. But in this case, I am using a machine learning model to predict the possession value or the value that should be assigned on every action on the pitch. And that is called the long short-term memory deep neural network to predict the probability of an action leading to a goal. So here, the output variable I considered is the probability of a shot, and also I use the independent variables like the coordinates or the location of the shot, as well as whether the player is under pressure or not under pressure. What was the current situation at that time when a pass or a carry or a dribble was made at that situation? So I use two things in order to predict my expected threat. I use first the probability of a shot given the sequence of actions and also the probability of that shot ending up in the goal. So I use StatsBomb data. They have a wide pool, a repository of data at their disposal that have events data on soccer. And I got all those useful information from the StatsBomb data repository. And that also helped me to come up with the expected threat. So here, the expected threat is trying to multiply the probability of shot by the probability of goal given the shot with regards to the coordinate or the location of the ball on the field. Yes, so I know I've been talking a lot about what the model is about. Now let's look at how the model was put into play. Let's look at the model in action. I would quickly want to show this video for you to see. And I used the data on the recently ended Euro 2024 championship, which Spain were the overall champions during that time. And I used that data in order to analyze possession value. So in the course of this presentation, all the analysis is centered on the Euro 2024, and all the insight and analysis were centered on that. So this is a quick video showing how possession value changed over some streaks or chains of possession. And this was during the finals in the Euro 2024, Spain versus England. And I want you to see a very quick video of that, and we'll speak to the analysis. So that was the possession leading to the first goal in the second half of the game. And that was a pass laid by Lamine Yamal to Nico Williams on there. So it was a pass that shifted the defensive setup. And Lamine Yamal's pass to Nico Williams added about 6.3% to the entire possession chain. And it was very pivotal in giving Spain that ultimate goal on there. And I would want to see a screenshot of how the event pan out. During the first frame you can rightly see on there, the first frame was when that pass was laid to Lamine Yamal at the central third of the pitch, and that pass was moved by Lamine Yamal into close to the 18-yard box, and that movement shifted the defensive shape of the English team, and that created a lot of space for Nico Williams on there to reach to the ball and just score the goal. And that was it with regards to the possession in action. So Lamine Yamal action on the pitch actually added 6.3% to the entire possession, and that was very pivotal in them scoring this opener in that game. And another scenario where you can also see that possession value does not only capture passes that move forward, but it also captures passes that are very essential, especially even if it's a backward pass. And you can clearly see from this video that there was a pass late to Thomas Muller, who sent a bad pass to Emil Chan to score this goal. And in this possession, the pass by Thomas Muller, even though it was a back pass, was rated 4.2% per the model I used. And that was quite significant in a way because it wasn't just a back pass, but it was a pass that essentially led to that goal. And that was one important thing. So using these two scenarios, so the first scenario was just all forward passes leading to the goal. In this case, there was a back pass, and the machine learning model I'm using also captured that back pass and valued it very high as compared to what other models would probably look into. And here I was looking at the expected threats during the Euro 2024, which team actually had the most expected threats in the attacking of half of the field. And guess what? It was so evident, it was so evidential to find out that Spain actually dominated in terms of the cumulative expected threat throughout the entire tournament. And excuse me, England also performed very well during that time. But one significant visualization I want you to see is that of Albania, where you can clearly see they were like the odd one out, where they didn't look pretty much threatening at the attacking half. And that is what happened during the Euro. And with regards to Portugal, you can clearly see they achieved a lot of expected threat at the wings, at the attacking flanks of the pitch, where they had guys like Rafael Leao and also Bernardo Silva, who were operating on the left and right wings. So they had a lot of expected threats coming from those directions. And that was what was captured. And Jude Bellingham was among one of the top players who had huge influence on the game with regards to the expected threat. He was penetrating into the defense and laying in all those passes that were ending up in some threatening zones that were likely to result in a goal. And it was interesting to map up a scatter plot to show which players had the most expected threats throughout the entire tournament. And guess what? Tony Cruz, who is noted to be a very creative player, was higher on that scale. He had the most successive passes and also the most expected threat. This is to say that he made lots of passes that ended up in dangerous areas where his team could potentially score a goal. And it was interesting to find some players, some defensive players like Kyle Walker and also Elmerick Laporta, who are all products of Manchester City, and they all learned under the tutelage of Pep Guardiola. And we know Pep Guardiola of Manchester City is a type of is a type of coach that have a very progressive mindset of play. And it's no surprising to see that he has two players on there who have actually worked with him, and they have high expected threats on there. And they are both defenders as well. So it took me to even proceed further to understand why Laporta was actually on top in terms of progressive passes as well, not just being successful with all those successful passes, and he was also successful with progressive passes. And here, the top five players in the entire tournament who had a lot of expected threat, they had maximum expected threats, where two were actually defenders, and it was surprising to me. I think the game has changed where defenders are actually involved in the attacking phase of a team's progression, where they are also part of the team's progression. So here, Laporta started off with Manchester City and currently is in Saudi Arabia playing somewhere else. And during his time with Manchester City is noted to have a lot of progressive passes and known to have a lot of build-up plays ending up in a goal-scoring opportunity. And it was no surprising to also see these two players on there from Manchester City who gave a lot of progressive passes, and these passes were pretty much threatening in a way. And Tony Cruz also represented them, Fabian Ruiz and N'Golo Kante also were represented very well on there as some of the players who did very well on the progressive passes. And two teams actually caught my eye. So I wanted to do a pass network to understand the setup of these two teams. First, I wanted to understand the pass network of England and also Spain. So this visualization show the pass network of Spain and their setup, their formation during the game. And the bigger image you see on there with the pass network is on the in the finals during the finals, and you can clearly see that they achieved a lot of possession value during the passes between Laporta and also the other defender on there. So during that stage, they were gradually building up from there. So that's where they achieved most of their expected threats on there, and you can clearly see with the centralization, they had. With this pass network, the centralization essentially tells the story that how much did they rely on a player, or was it a very collaborative effort by both teams? So the higher the number of centralization, then it means they relied mostly on some specific players. If the centralization is lower, then it means they actually were very pretty much collaborative on the field of play. And Spain did a very good job with that, with a centralization of 0.0934 on there. So and they had a lot of progressive passes ending up in the England's defensive third, and that is where they achieved most of their expected threat from. And this was just from visualization to show how they transitioned all the way from the group stage to the finals. How was their defensive setup, their formation setup like? So you can clearly see during the group stage, they were pretty much wide open on possession. And they started narrowing down during the knockout phase where they start getting together on there. Also, with the England setup, it was very interesting to find out that most of their attacks or where they achieve a lot of expected threats, looking at this visualization where the thickness of the bar suggests that they had a lot of passes on there, and also the brightness of the bar suggests that that is where they were achieving a lot of expected threats. So you can clearly see that the pass between Jude Bellingham and also Hurricane was actually the spot where England achieved a lot of expected threats. So the combination between Jude Bellingham and also Hurricane were the spots where the England achieved a lot of expected threat, and they also achieved a very good number of expected threat from their right side of attack, where Bukayo Saka and also uh, and Bukayo Saka also was actually there, and that is where they achieved a lot of expected trade on there also. And you can clearly see, as compared to Spain, Spain had a lot of progressive passes, but England did not necessarily have a lot of progressive passes, but they looked threatening away. And most of their progressive passes were towards the direction of Bukayo Saka, and that is where they achieve a lot of expected trade going forward to attacking. So, looking at the game, I wanted to understand how was the build-up play like, and also how was the progressive passes looking like for the two teams. Still, we are using the finals as a case study. That is Spain versus England. So, I wanted to look at the build-up phase, the progressive passes phase, and also the defensive expected threat they posed in the game. And clearly, you can see during the build-up phase. England actually slightly dominated at the build-up stage where they did pretty well whilst moving the ball. So build-up phase, to those who are not confident with build-up phase in the game, is just essentially moving the ball in about 10 meters from the defensive third to the central third of the field. So any gradual movement that is like 10 or 5 meters in length is considered a build-up play. It could be a backward pass, and that is potentially a build-up play. And England dominated in that field, but it was just marginally, but it wasn't a huge dominance on there. And progressive passes, Spain was actually totally dominated with regards to progressive passes, giving all those progressive, exploiting the loopholes in the England
Hey,
defense, laying
Daniel,
all those good passes on there. Yes.
I didn't want to interrupt, but I think you're at time. So if you want to just say like one more thing and then we'll have to move
Yes.
on to our next speaker.
Yes, you can. So at this point, with regards to the defensive, that is what is clearly seen on the defensive side and also the offensive for both teams. So, So there's a lot to talk about with regards to the players in the possession, and I believe that this analysis is essential for coaches as they would understand the performance of the team and know which plays to start working on in order to improve the performance of the team. And to the fans, it's very important to understand that the players are very unique and they have their own unique abilities, and we should remain relaxed whenever things are probably not working out because the team is not scoring does not mean they are not performing very well, and that you should consider the individual performance and individual brilliance of the team, the players as well. So that is it with my presentation. I know I had a lot to talk about, but it was a little bit brief. Yes.
No worries. Thank you. I guess I'll let people send you a message if they have specific questions, if everyone wants to, give the little clapping reaction to say thank you, and then we'll introduce our next speaker. So next is Mike Schuckers. He recently joined UNC-Charlotte as a professor of sports analytics and data science. And before that, he was a professor of statistics at St. Lawrence University in Canton, New York. And he's going to be talking to us about the SCORE network, connecting sports data to statistics and data science classroom. So Mike, if you want to go ahead and take it away.
Awesome. Thank you, Kendall, for the introduction. Thank you to Russ for all the organization and the hard work that goes into doing this. And thank you, Samuel and Kendall, for your talks, interesting talks. Unfortunately, maybe I'm not talking about soccer. I'm going to be talking about SCORE Network, which is an educational project. We're trying to connect some sports data to the data science and statistics classroom. And there we go. I'm just crediting somebody for the slide materials here. So the SCORE Network, SCORE stands for Sports Content for Outreach, Research, and Education. It's a multi-year grant funded by U.S. National Science Foundation, multi-institutional, some of those institutionals there, and yay team, we can add Charlotte to that as of about 10 weeks ago when I joined UNC-Charlotte. Our goal here is to develop and facilitate development of stat and data science educational materials. We have a focus on sort of non-traditional sports, so the sports that don't receive a whole lot of attention in terms of analytics, and women's sports. Again, the idea here is to broaden the pipeline of students who would be interested in statistics and data science, and we want to generate curated educational content. And there's our little logo. So I probably don't have to say this part of it to this audience, but sports is broadly popular. Students who come often come with subject matter knowledge and interest and questions. And hopefully the things that they learn in our classrooms are transferable to other environments. In many ways, sports data is a very controlled environment, which means that it's easy to jump in, right? Our rules are mostly the same over time, but there's a lot of interesting and varied problems, from the problems that Kendall and Samuel are talking with, but also problems on the business side and maybe player acquisition side. Sports in education, that kind of makes me uncomfortable. I'd like to quantify that, but many educators already use sports in their classroom. The need here is to have a structure and a standardization of those materials, provide a pedagogical framework, a centralized repository. And one of the things we wanted to add was an industry and media perspective, and create some incentives for our author educators here. And so that's really where SCORE comes in. So our SCORE model is to have open-based, peer-vetted, and I'll talk a little bit about what that vetting looks like, case-based educational materials. And then there's really nothing unique about that, but we're going to add the sports and the statistics and data science piece. The basic building block of these materials is what we call a module. So a module is self-contained. It's meant to be plug and play. We have a module I'll talk about a module on correlation in a couple of minutes, right? That material is meant to be able to just drop into any class that is covering that material. We want those materials to be engaging and motivating. And so we will have an introduction that hopefully motivates and hopefully addresses a relevant problem. Here we're trying to employ educational best practices in statistics and data science education. That's a GAZE framework. We want accessible and inclusive language because we know that not everybody loves sports, and also not everybody knows a particular sport to a level of detail. So we want to make it so that, right, if I'm doing a module on badminton or I'm doing a module on esports, right, that the language that we use there makes it usable from everyone. And again, that pedagogically sound is a big deal because we are all educators, and this is meant to be educational material. Briefly, I guess not briefly, but the content of each module, we have a motivational and introductory video. Talk about that in a second, but we have clearly stated learning goals. We have the methods or description of the methodology that's being used, data set or data sets, a data glossary, some notes, some handouts, some exercises, whatever is part of that. And then we like to have a conclusion and a README file. So part of what we are doing is encouraging people to generate and create modules. And so everything there, but the video at the beginning is something that we expect when someone submits a module to score, to be evaluated, to be vetted. The video we can help with a little bit, and that can come later on in the process. So talk a little bit about peer vetting. This is much like peer review, but it is non-adversarial, right? So we want to be rigorous, but we don't want this to be a battle in terms of publication. We want to get these modules out and published. And so the goal of the review process there, we want to use diverse experience skills of the people in the SCORE network, provide feedback from multiple perspectives. And so for each module, it is reviewed by someone in that particular sport industry. It's reviewed by someone with a strong pedagogical background. And it's got the standardized format, and talked a little bit about format in the previous slide. We do have, for that review, for our vetting, we do have the usual sort of journal structure. So we have editors. I'm one of two current editors. The other is Nick Clark, and I'll mention Nick later. We have some associate editors. We have reviewers. And the reviews that we look for are pedagogical, as I mentioned, industry. And then optionally, we try to get some student feedback. Obviously, this is our target audience. And so we want them to comment and tell us, right? Often we think we make great materials, and the students come back and say, yeah, maybe that wasn't as fun or as engaging as you thought. I'll go into some detail and pull up some modules, but just to give you a couple of examples, this is a module on correlation between events in the women's Lake Placid Ironman. This is Sarah Groff True, who represented the US in a couple of Olympic triathlons, and was the winner of the Lake Placid Ironman, for which we have some data. And Sarah generously has recorded the introductory video for that particular module for us. Another example is we have a module on League of Legends data. And the data here, we're looking at win rates in different patches. For, I believe in League of Legends, it's champions, but the characters that you play. And the idea is, right, the makers of League of Legends, are they nerfing and buffing? Nerfing means to weaken a character, and buffing means to make them stronger. Again, right? Need that as part of our background information so that everybody's up to speed on what we're talking about. But we can look at, one basically version of the game and look at which champions stand out. And then are they standing out in the next version? And we find that they're not. And so, someone who is generating these versions is updating and changing the character strengths, to make things more fair in some sense. We have another module on transformation of variables. Sometimes we want to transform variables to normality or to some other distribution. And so in this case, we're doing some variable transformation with some NASCAR data. So there's another module. Again, right? All three of these examples, not your traditional football, baseball, basketball, soccer, and hockey. Again, with the idea of sort of broadening the interest of individuals in statistics and data science. So let's see. Gonna do a little exploring of modules. Let me see if I can do this. And I'm gonna ask Kendall. Kendall, do you see no longer see my slides? You see some
No,
screen?
I just see your slides still.
You just see the slides. Well, then we'll do the stop share and reshare. Thank you for that. And just pull up. So here is the score
We
network.
can see it now. You're good.
Yeah, thank you, Kendall. So here's the Score Network webpage. Scroll through there, a couple of example modules. Couple of things in our little hamburger menu over here. Some things about us and the projects. But we've got a module repository. We are currently at approximately 25 accepted modules, and we have about another 50 that are in process. And we also have a data repository. I think I have a slide there when we come back on those. What I wanted to do is just sort of walk you through a couple of modules. So just going to walk you through the League of Legends modules. So first of all, this is the module repository. We have modules by sport here. And we can also, well, I'll come back and talk about that in a bit. But here is our League of Legends modules. We've got the authors, we've got the date published. Here's our introductory video. This one was done by the captain of the esports team at West Point. Little bit of introduction and background on the module, and in this case, League of Legends, the sport. Learning objectives there. Again, right, we want this to be a very intentional process here. And so we want to be clear the learning legends, I said it again, what the learning objectives are for this particular module. The methods here, right? So we're talking about looking at histograms, identifying outliers, right? Some rules for that. We have data. This is the patch. So this is version 12.22 and version 12.23, and we can start to take a look at that. The materials that come with it is a class handout and a class handout with solutions. And we've got a conclusion there, and students can come back to this. Class handouts, usually in some sort of format that faculty then can modify to their class. And so we want something that is flexible, right? I might talk about outliers, right? Traditionally, I only talk about the 1.5 interquartile range rule. Other folks I know do both that and say a z-score rule for outliers. Obviously, with this material, you can go in, modify it as appropriate for your class. So there's one module. This is a second module. This is the module with Sarah True in it. We've got that video, little bit of introduction. This is a piece of software that is housed at Carnegie Mellon called ISLE, Independent Statistical Learning Environment. And this has just got a bit more structure to it. And so we've got the introduction, the data description here, all of the variables that are there, and the data source. Again, intentional about learning goals here. Methodology, we're going to do some scatter plots and some correlation. Materials, so we've got some data and we've got a worksheet there. Right. Conclusions, what we want students to be getting out of that. And in this case, this structure has the author information at the bottom. Let's see. While I'm here, just mention, right, we've got modules by sport there, but also we have topics for the module. So interested in a Poisson process model, or some bimodal data, some histograms, those sorts of things, you've got that. We have a preprint or a set of preprint servers there for the modules that are in progress. We know as we are building this network, so we're in the second year of a 4-year grant, as we are building this network, we want to try and get those materials out as quickly as possible. We've also got a data repository, which is larger. Our data repository is about 80 data sets right now. So we like to have every data set that's in a module also in the repository, but we've also got some other data sets that are not yet in modules in that repository. I'm going to go back to my slides for a second. There we go. Just talk a little bit more about the network. So I mentioned that some of the institutions that are involved, Carnegie Mellon, University of Pittsburgh, Baylor, St. Lawrence, West Point, Yale, and now UNC-Charlotte. We've got members and industry partners. So industry partners are folks that help us build out those modules and do the industry review. And so lots of those come from sports teams or individuals that are affiliated with sports. And I've got a note from Amelia's keynote earlier that I've got a lacrosse module, and Amelia would be great, I think, to be a reviewer for that. So here's where we are right now, data repository. I mentioned number of modules and more we've got in review. They're tagged and they're searchable. We're always looking for reviewers. And I mentioned that we want to give credit to authors. So we are viewing these modules as sort of like mini publications. They are indeed peer reviewed and peer vetted. They take a lot of work. And we're going to start adding DOI indices to modules with the idea that we would hopefully get people credit for the great educational materials that they're doing. We also do some analytics and we track some downloads. So if you're producing a great model that is being used by hundreds, thousands of people, then we can track that and we can give you credit for that. Here is my list of collaborators, long list there across many institutions. And I think I failed to mention Azusa Pacific there when I was talking earlier. But again, some really great names in statistics education, part of that group. And then last but not least, this is the QR code for if you want to join the network. And so joining the network as of now, we're going to send you updates probably a couple of times a year, highlighting some of the things that have been added to our data and our module repository, as well as making yourself available to help us review modules and getting you information to help you create modules if you would like to do that. And be part of any presentations or workshops that we're working on. And I think with that message from Russ, it's a good time for me to stop and take questions. I can get to my stop share. There we go. Awesome. Good. Is that a raised hand, Russ? Go.
It is a raised hand. So question, I was poking around, and I've known about your project for a little while now, and I was poking around on your website, and I noticed the description. And please don't take this as a criticism; it's a genuine question. The topics that it seems that there are modules for seem almost exclusively statistics. Is there a push for more sort of data science kind of topics, or are those really weave together? Because I know that there's the lines are blurred there. I get that, but
Yep. There's at least 2 modules that I know of in process that are on things like data wrangling and on doing some joining, sorts of things that are more data science than statistical. But you're right, it is an area that we are actively working for and actively looking for more modules to be created.
cool.
So, yep. Well, with that, just kudos to you, Russ, for doing this again this year, and thank you for all the work. It's been great.
Thanks. Awesome. Well, y'all still have like 45 seconds if somebody has a quick question, but I'm going to head to the main area here and yeah, this is really good talk. Thank you very much.
Yeah.